tomorrow? Anyway, we can check
Okay.
afterwards. Okay, so I'll be talking about our work with Amr on partial interference effects. But before we get into what partial interference effects are, let's talk about quantum interference first. So, quantum interference is one of the first things that many quantum textbooks and classes start with, the famous double slit experiment, not only because it is a very interesting thing, but it is also one of the core ideas that power the quantum algorithms, the ones at least that we know of so far. So quantum state and superposition can either build up constructively through interference. So if I have the same state psi, I have alpha and beta as the amplitudes, they will add up constructively. But if they're of opposite signs, then they will diminish through destructive interference. And if the magnitudes are the same, this will cancel out. So we have a basic Dosh-Josa circuit here. And at the bottom, I have the vector formalism of how this state evolves throughout the circuit. You know, the first Hadamard on the first qubit, second Hadamard on the second qubit, and so on. But where is the interference here? Well, turns out in this formalism, the interference is almost implicit. It is buried. And it is buried in matrix multiplication. So if we look at the application of the second Hadamard gate on the first qubit, the interference technically happens when you multiply all the columns and the rows and add things up. So here, for example, in the first part, I have two amplitudes of opposite sign, and this cancels out. Let's look at another example. This is a Simon circuit for n equals 2 and a equals 3. And I have a total of 4 Hadamard gates, so 2 to the 4, I will have 16 intermediate states. And 4 of these are the outcomes that I will accept to some extent. 0, 0, 0, 0, 0, 0, 1, 1, and so on, where depending on the measurement of B0 and B1, getting 0, 0 on the first 2 qubits will mean that the circuit will need to be restarted because 0 has a specific meaning in Simon's problem. And if I get 1, 1 on both qubits, then that is the answer that I'm looking for, and I'm happy. But instead of using the vector representation, that is the classical textbook way of doing this, let's look at this problem through like an execution tree. So what is happening here is essentially I have the circuit on the right, I am applying the first Hadamard on the first qubit, and I'm branching the execution out. Same thing for the first Hadamard on the second qubit, and I have the black box oracle that encodes the function itself, and finally the final 2 Hadamards. The states that I've underlined blue here are the ones that I mentioned early on that are somewhat acceptable for us. All those zeros means, again, the circuit needs to be restarted. And these will go through either constructive interference or destructive interference. The blue arrows here signify constructive, and the red ones signify destructive. For a moment, let's focus on destructive interference. So I have the state 0, 1, 1, 1 here. It appears twice, exactly twice in my tree. And the 2 occurrences are of same magnitude but opposite sign. So when these 2 states interfere, this state will basically disappear. It will not appear in my probability distribution. There will not be a way for me to sample this. That is, of course, theoretical. In practice, if you have noise, things can be a little bit different. But there's no way for me to sample this in theory. If this thing is going to disappear anyway, what if I didn't have to compute that anyway? Because it just seems like wasted work, right? I mean, it's going to disappear from my probability distribution. It is of no use to me, so why am I doing all this work? One, you know, it is a computational step that adds some amount of complexity to my program, and 2, it is something that I have to store in memory. And here, it's not too bad, but there are problems where less than 10% of these intermediate states actually are the things that I care about that will be building up constructively, and there will be hundreds of millions of intermediate states as my circuits grow larger. So maybe I can save a little bit of work if I'm clever. But of course, I don't know the answer ahead of time, so there's no way for me to sort of handpick these things. But perhaps we can do something a little bit clever to turn tides in our favor. So the question we're asking is how much computation can we actually save on if we were truncating the branches that we didn't need? There are three crucial observations. One, as I stated earlier, the cancellation of amplitudes through interference is essentially the same as not doing that work in the first place. Two, again, the majority of the interference computations will be worked towards destructive interference, and very, very little in most cases is interference that I care about. And three, many quantum algorithms function by manipulating the amplitudes to favor the correct results. And this is because, of course, were you going to take a picture? This is, of course, because our quantum algorithms are probabilistic, and this execution of Shor, we still have a chance of getting the incorrect result and rerunning the circuit. The way I like to visualize this is through a membrane model. So going back to our tree, we're going to make everything concurrent. So all of these new branches will spawn a new thread of control, and everything will be executing concurrently. So here, T1 through Tk are different threads of control. The half-filled circles mean that it is still doing some computation. There's still more gates in my circuit to apply to the local state. And the red ones, which are in majority, are the states that will disappear through destructive interference that I don't care about. And the green ones are the actual results that I would love to sample. And as these threads finish their work, they will push these results through this membrane, into this box. And as they enter this box, they will randomly start interfering. So if I have A and B on the state 1, it will become A plus B. And similarly, if I have A minus A, this state will completely disappear through interference. And if this was completely synchronized and we waited for everything to finish, this would be exactly the same thing as a textbook vector formalism of this kind of computation. But the fact that this is a concurrent operation and things can happen in randomized orders give us a new degree of freedom. So what I'm going to do is I'm going to pick some threshold x for my amplitude, 0.25, 0.1, depending on the problem. You have to be careful on how you pick this. And as soon as any state that makes it into this membrane reaches that threshold, I'm going to halt all the other ongoing terminations. There will be threads that haven't finished their work, that haven't pushed their state into this membrane yet, but I'll say, okay, I don't care about this. I'm going to stop here. And of course, whatever has made it in, the amplitude square will not add up to 1, so I'll have to rescale, and I'll sample from this subset that I have here. Going back to the observations that I've stated, per observation tree, which as a reminder is the one about most quantum algorithms manipulating amplitudes to favor correct results, a correct state that is a green state will have a higher probability of triggering a membrane shutdown than an incorrect one. So think of Grover, the amplitude of the correct result is much higher than the incorrect one. So if my threshold is high enough, then a correct state will trigger the shutdown. Per observation 2, when the membrane shuts down, because the ratio of states, the undesirable states that will disappear is much higher than the correct ones, a lot more of the states that I don't care about will be left out, and I will only lose very little of the states that I care about. And per what I stated above, again, if the threshold is high enough, we can guarantee enough correct states can get through for us to sample the correct outcome. Turns out this is very similar to a model of concurrency that already exists called chemical abstract machines. This original paper dates back to the 80s. It is a classical reversible model of concurrency. And chemical abstract machines model computation as the global evolution of a collection of atomic states that randomly interact with each other. So these molecules can essentially collide, like think of an actual chemical solution where molecules hit each other and go into a reaction or not based on compatibility. If they're not compatible, the molecules will just return to the pool. And if they're compatible, they can combine to create a new one with higher amplitude, or they can, molecule can decompose to create multiple smaller ones, which isn't all that applicable here. So here's the algorithm. We start a solution with our input state to the circuit. We place special step molecules into the solution. And when the input state hits the first one, it applies the next gate in line, which, if it's a Hadamard, then we will return 2 new molecules to our solution. And if there are no more gates to apply to that local state, then it is marked specifically to be ready for interference. And when two marked states that come into contact, if they are compatible, they will interfere to build up constructively, or they will diminish destructively, and no molecules will be returned. And after a specific reaction, if the molecule that is being returned to the solution has an amplitude that is greater than the threshold that I've determined, I will stop everything else. I will rescale my amplitudes, and I will sample from this subset. So we tested this on Grover for searching text states as well as different instances of three-side problem at up to 8 qubits. We were able to get 86% accuracy for 0.7 threshold. That is, we didn't do 30% of the work, and we still got good results. And again, I'd like to remind you that maybe not so much for Grover, but the quantum algorithm itself is also probabilistic, so it doesn't give you the correct result 100% of the time. So in comparison, 86% is pretty good. And even for something absurdly low, right, 0.1 threshold, we were able to get 30% accuracy. This isn't all that surprising for Grover, because Grover specifically has a very, very large difference between the correct state and the incorrect outcomes. And when we leave a lot of these incorrect outcomes outside the solution and don't allow them to build up too much, this difference grows even larger. And for something 8-qubit three-side problem, we were able to save up to 200,000 computations for low thresholds and 60,000 for high thresholds like 0.9. We also tested this on Simon and Shor. Our accuracy here is a little bit lower than Grover because the results are much closer to each other. We tested this for Simon with k equals 3 and k equals 4, and Shor for n equals 15 and n equals 21. Shor is probably the more interesting one since it has a lot of Hadamard gates. We were able to save up to 10 million interference computations for lower thresholds and 1 million for higher thresholds. That's the accuracy. That's the percentage of the result being returned, being the result that you're actually looking for. That's the threshold. So I'm going to, as soon as I get a molecule in my solution, for example, that has amplitude 0.5, I'm going to stop my computation. So as the threshold increases, the more interference patterns you calculate, and the more molecules make it inside, and understandably, your accuracy of picking the right solution increases as more of them disappear. But this is a really question of how much efficiency can we gain by sacrificing how much accuracy. So in conclusion, we're presenting a novel technique for simulating quantum circuits that uses concurrent trains of control to expose a fine-grained control over the interference computations. As opposed to well-established simulation methods like Feynman's sum-over-pat integral method, we can greedily and concurrently build up these histories and eagerly terminate when we feel confident enough that our results will be fine. And we noted a good increase in efficiency of these simulations, again, up to millions of computational steps saved by sacrificing very little accuracy. For future work, we want to try to apply this to something like boson sampling, which is known not to be simulatable classically. We also hope to investigate the role of noise in a model like this, in a simulation model like this. We hope to explore the physicality of this model. Nature is concurrent itself, but our quantum computers require a high level of synchrony. So I think it's an important conversation to have. We hope to consider probabilistic reaction rules, and we also want to consider algorithm-specific optimizations. This method is as generalized as it can be. You can just download the code, put in whatever circuit you want, but perhaps there are further optimizations that can leverage the specifics of these algorithms. For example, Grover's algorithm requires multiple iterations, and this is because we rotate every time slowly, and each iteration puts a larger gap between the amplitudes of incorrect states and correct states. Well, another way of increasing this gap is essentially by omitting some of these undesirable states. So we hope to investigate, for example, can we skip some of the iterations by using this simulation method, because that would be huge, and that would save us a lot of computational power. That is all I have. Thank you. keep for questions.
Okay, so I'm very interested in what you said about let's decrease all the way down to 0.1 and we get a low success rate. However, we can do it again and we can do it some more times. That could increase the success rate back up to like 50%. So do you have any, assuming that it's independent tries, right?
Mm-hmm.
Did you do any sort of calculation of that if we are going for a 50% success rate, we decrease the initial success rate and then we repeat? How does it compare at that point?
So the stats that I presented are mean over multiple runs. Obviously, one trial is insignificant, so we did multiple times. But unfortunately, I do not have the data for the variance of those things, because I think that's what you're trying to get at. That is, if we run the 0.1 multiple times, can we get? Yeah. We haven't done that, but it is an interesting point.
It could be that we'll still come out way ahead.
That is true. That is true.
How much does the amount of computation scale with the threshold? Is it linear? That is t equals 0.1 10 times faster than t equals 1, or?
So it is it is very difficult to formalize that, and I'll say why. Because of the randomized nature, it is. I think it would be interesting to figure that out. But what can happen is, like, even let's say for 0.8, it is completely possible that the first 2 or 3 intermediate states that make it into the solution are the green ones, and that will immediately build up to your threshold. If that's the case, you will save, that's the best case scenario, you will save a lot of work. But it is also possible for low thresholds that the first few that makes it in are the red ones, then you will have to do a lot more interference patterns. I don't have a direct answer on how it scales mathematically, but the point I'm trying to make is it's kind of hard to formalize that because of the randomized nature of what makes it into the solution first and later.
Yeah, I guess you could try to run it and see what happens in expectation.
Yes.
Have you tried that, or?
No, we haven't.
No. Okay, thank you.
I just have a question on this, again, threshold thingy here. Since we're talking about the amount of work being done given the number of inputs that come here, for example, for like 0.8, you were saying like T1, T2, T3 are such that it hits like the 0.8 threshold that you wanted. But wouldn't the work you would, like, what would you classify as work here? Would it also be the multiplications that are being done to get to that stage, right? And when all the threads are being run in parallel, so I was just confused because, like, I was thinking, like, oh, wouldn't the other thread still be doing the multiplicative work even though the addition work is
so,
the one being saved?
One thing I think it is important to clarify is here, the truncation specifically happens in the last nodes. We're not, obviously cutting off the entire path because those paths also lead to the states that we care about. So the work that we specify here is in terms of how many interference calculations that you have to do. The paper itself has a more detailed table on the total number of interference, the intermediate states, the number of states that you care about, and the number of states on average that our simulation method used. So if you're curious, you can check that table for more detail.
And just one follow-up on that, is it possible then, like, for certain algorithms that you might have seen, like, where this kind of an approach can be used intermediately because there might be multiple case places where destructive interference takes place in particular? Maybe for, like, multiple growers, algorithm runs itself, but, like, that's
that is entirely possible. As I said, it is one of the things that we want to look at on leveraging the structure of specific algorithms to further improve these results. And as you said, Grover is the prime candidate for for that.
Yeah, thank you for the talk. In many simulators, they do something, some pre-processing that is called gate fusion, which basically means that you collect certain gates together into one unitary that is like not super huge, but also not super small. And by that, you basically reduce the amount of unitary applications that you have. And actually, I think in many algorithms, not only in Grover, you have unitaries that basically only permute the amplitude, so they neither introduce superposition or destroy superposition. So maybe that could also be a way for you to like have a specified gate fusion, basically by looking for this kind of gates and then executing them first, and then if you really have to, then you do your interference logic.
Right. That is something I would have to look into. It sounds great. Intuitively, one thing I would say is I think when you're doing that kind of gate fusion, where you're multiplied the matrices of the gates themselves, perhaps the metric for work might need to change because you're adding a different kind of work. So the what kind of computation you saved, that definition might need to be altered a little bit to account for that extra step. We haven't put it up anywhere, but it will go up. Yes, I mean, there's obviously something that was submitted, so yes. It has better results, more detailed results.
No? Okay, then thank you.
Thank you.